So our last speaker, the name should be presented by Ana Maria Garcia Amarillo, but she's not here, so Giorgio Bardizza is going to present her talk, and it's about energy rating studies of different organic PV devices in different climate conditions.
Okay. Thank you, Monica, for this kind introduction. Unfortunately for you, I'm not Anna, but Anna is following online, so she's checking if I'm doing the job correctly. So the work I'm presenting here is mainly the work that Anna did in the calculation, particularly of this energy rating study. But my name is this one, so I'm Giorgio Bardizza, and I participated, as I say, in this work, performing mainly the measurement, which are one of the input of this study. So with the talk we had this afternoon in this nice session, I think everybody is very well convinced that there is space in the future for OPV to be outside, maybe together with silicon, or hopefully maybe also in place of silicon. We've got a really nice talk this afternoon on this issue. I'd like just to add something that probably you know already, but anyway, there are companies which are producing already OPV modules in large dimensions. There are systems with OPV modules set up outdoor, which are running, which are producing energy. So I think there is the need of testing these devices in real working condition, and this is exactly the objective of this talk. So we analyze the performance of different OPV devices and the real working condition in 5 different locations in the world. And we try to compare this with the same, with other more established PV technologies, crystalline silicon, obviously, cadmium telluride, and amorphous silicon. And yeah, and I will show you the results at the end and at the poster, obviously. The input data of this study are 2 mainly. The first group is is based on the PVG system, which has been developed within our laboratories, mainly by Thomas Huld, which is one of the authors of this work. But also Anna is working together with Thomas in performing different type of energy rating studies, taking the PVG's data as an input. And the PVG's data are mainly irradiance. Now is mostly the entire world inside the PVG's map. They have the optimal angle as the data, and they have data related to weather condition and also ambient temperature and wind speed. The other part instead, which is input of this study, is related to the job I did, which is the power metrics measurements performed on the devices that I will show you shortly. The power metrics measurements are performed in different combination of irradiance and temperature. And yeah, obviously these are performed with the devices that we managed to receive in our laboratories. In the future, we will perform a similar study with more professional devices, and so we will put some more weight on this hopefully. What is an energy rating study? An energy rating study is a way of estimating the performance of PV modules. There are different other ways. Normally, if you want to compare the performances of your device at standard test condition, you measure it only at standard test condition. Or otherwise, another very good way is to perform an energy yield prediction. But this needs a long time, because normally you need real measured data in a long term. You need to take into account effect of shadow and snow or dust, for example, and you need to take into account the degradation. This is very, it's much more complex, and we are not ready, obviously, with the OPV to do this kind of study. But what we can do at the moment is, for sure, instead an estimation of the performance ratio of PV devices using an energy rating. Just to tell you that soon will come out a new standard with the energy rating as included in one of these. So the method is now some way recognized by the community, and is based on the module performance ratio, which is the ratio between the total module energy output in kilowatt hours and the total in plane irradiation during the same period, multiplied by the power of the module at standard test condition. Normally, they are based on 1 year of hourly data, at least the one we performed in our group. These are the devices that we tested, and these are, as I said before, the basis of this study. So, are 2 devices provided a few years ago by Professor Krebs and his group, and another one which was bought from Infinity PV more recently. Yeah, that's where the devices, I think you know them very well, so I will not enter in the details of these devices. But I will enter in more detail instead on the methodology that we used. This is the power model that we used to fit the power metrics data. And fitting this data, we got these 6 coefficients that have been used afterwards with this model to estimate, so to calculate the power output at every combination of irradiance and temperature. And this G here in the formula is the in-plane irradiance. And as I said before, we take into account the ambient temperature, which influenced in some way the temperature of the model, taking into account the temperature, the ambient temperature, the irradiance incident into the module, but also the wind speed. So how does it work? We take into account, as I say, the angle of incident effect, which is maybe related to the spectral effect of the spectral response of the devices. We, as I say, take into account the temperature using the Feynman model, which gives us the temperature of the module by the temperature, ambient temperature, and the wind speed. And we fit the power metrics data where we calculate the key factors that we use afterwards in the calculation. We use 1 year of hourly data taken from the PVG system. These are the locations that we used in our study. So there are locations going from Scotland, north in Scotland, and south in Gabon. And these are the angles, the optimal angles that came out from the study, and the one that we used, obviously, for the study. And these are the results. So in this plot, I'm plotting the module performance ratio in the different locations. With the different colors, you see the technologies that we study. In the blue colors, you see the OPV devices, while in red, green, and orange, you see the more established one. What is interesting to see is that, particularly in the location where the climate is hot and the latitude is low, OPV is performing quite well. Comparing to the other technology. The amorphous silicon seems to outperform all the technologies, apart from the blue one, the light blue one is the devices which was bought from Infinity PV. And this one, in fact, seems to outperform all the other OPV devices, but also all the other technologies, apart from Scotland, where instead the OPV seems to not be the right solution. But we are not so sad about this, because in Scotland there is not so much light, as far as I know. So I think we can survive with this. So in conclusion, I hope I managed to convince you with this presentation that MPR is a useful tool to perform this kind of study. I hope I managed to convince you that with the data, at least that we have in our hands, what these devices, OPV devices, are working better than other PV technologies at low latitude and the high temperature. Impressively, these devices, the new one we bought from OPV, is doing differently than the other OPV devices, but we believe a lot on this because it's more recent, higher performing, and more fresh compared to the other one. I want to stress that the degradation was not considered in this study. Obviously, this is an issue to take into account. And that this methodology has been proposed and will enter in the IC standard soon. So be updated on this topic too. Thank you very much for your attention.